Alright, lesson 2.4 is all about equations of lines and working with different forms of linear equations. And so I have a little grid here. Please copy it down. We have the name of the type of form and then the form itself, and then we're going to do a couple notes on when to use each form. So the first form is the one that we've been working with most of all. It is the slope y-intercept. Slope y-intercept form, and that's the most common one to us so far. It's a standard equation of a line, y equals mx plus b. So when are we going to use this equation of the line? Well, we can use this when we are given slope or when we're given the y-intercept. We really want to be given both of these in order to make this equation useful. Now, if we're not given the y-intercept or we're not given the slope, there are strategies that we can use that we've learned in past lessons that we can find these things and then express our equation of a line in the form y equals mx plus b in slope y-intercept form. The next form of an equation, which is very helpful, is called point-slope formula. Point-slope form. So just as we had here, we had the slope and the y-intercept. Slope, y-intercept. When we use this form, we're going to be given a point and the slope. So when we're given the slope, again, and when we're given a point. Any old point on the line, x, y. Those are the coordinates of the point on the line. And the form is this. Y minus y1 is equal to m times x minus xy. So you notice there's two y's and two x's, but we're only given 1 point. But look, we don't have a y-intercept out here. So this form is very helpful. We just sub the x value of our point for x1, sub the y value of the given point for y1, sub in our slope, do some algebra, and when we rearrange it, we'll actually end up with this form, y equals mx plus b, if we've done our algebra correctly. The last form is by far the least helpful when drawing or solving, but it's very good for solving an equation, and it's actually called the standard form. Standard form. And right now we're working with linear equations, but as we move on to quadratics or cubics and more difficult polynomial equations, this form becomes more and more useful. And it is like this. We have a capital A, which is the coefficient of our x term, plus capital B, which is the coefficient in front of our y term, plus C, which is our constant, equals 0. And again, this gets more and more helpful as time goes on. But here, A and B are not allowed to be 0 because we have to have an x term and a y term. And if A was 0, then the x term would disappear. We can't have that in the equation of a line because we know we have y's and an x in our equation of a line. And x and y represent real numbers just as they would in the other two forms. So there you have it. You have slope y-intercept form, which is our most familiar form. We have point-slope form, which is very helpful if we're not given the y-intercept, but we are given another point on the line. And then we have the standard form. Before we move on to our examples, it's good to review these two concepts, parallel lines and perpendicular lines. And the hint is right in there. Parallel has these two L's side by side. They are parallel lines. So this gives it away that the parallel lines are two lines that go the same direction. So if they are going the same direction, then that means they must have the same slope. They're not necessarily the exact same line. They don't necessarily have the exact same linear equation or formula, but they always will have the same m. They'll have the same slope. So for instance, if we had the line AB and the line CD, and these two were deemed to be parallel, we would verify that by testing to see if the slope of AB is indeed equal to the slope of CD. if this statement is true, that the slope of AB is the same as the slope of CD, then we can say that AB, it's the name of the first line, is parallel to CD. That's some of the symbolism that we're going to be using as we move forward. Well, let's talk about perpendicular lines. Let's say we have two different lines. This time we have EF, and we have the line segment GH. Now notice I didn't put GF bisecting EF, GH bisecting EF, because I don't want you to think that a perpendicular line has to cut a line in half. It doesn't. These lines are perpendicular because they meet at a right angle. Now if they meet at a right angle, and they make a 90-degree angle here, all four ways is 90 degrees, what can we say about the slope of GH and EF? Well, we need to say that these slopes have to be perpendicular to each other. They have to be perpendicular to each other. And the way that we do that and prove that is we show that the slope of GH times the slope of EF equals -1. Let's take an example. A real easy slope to work with is, well, let's use a fraction actually. We'll say that EF here has a slope of 2/5. So it's the rise over run. And let's say that EF has a slope of -5/2. So as it goes over 2, it's going down 5. And that looks to be approximately what they are, which is why I chose them. If we multiplied this out, we get 2 times -5, which is -10, over 5 times 2, which is 10, which reduces to -1. If this comes out as -1, then we can say that GH is perpendicular to EF, because the slopes, the product of the slopes of GH and EF is -1, as we saw here. The product of the slopes is -1. If that's true, then GF is perpendicular to EF. GH is perpendicular to EF. Now we've been using the phrase opposite reciprocal or negative reciprocal. So let's go ahead and look back at our slopes that I chose here. And you'll see they are opposite reciprocals. The sign over here is positive, so the sign of the perpendicular slope is negative. Here we had a rise of 2 and a run of 5. Here we have a rise of 5 and a run of 2. So that fraction is just flipped. It's just the reciprocal and the sign is opposite. And that is our review of parallel and perpendicular line segments. Again, before we take on example 1, go ahead and write the formulas that you know are in your toolbox that you can use to solve these problems, so that when you need to refer to them or use them, they're right there in front of you. So you should have recorded the standard formula that we've been using, slope y-intercept form of a line. You should be recording point slope form. You should also be recording things like the formula for slope, m equals rise over run, or the change in y over the change in x. Should be recording the midpoint formula, and you should be recording the distance formula for the length of a line segment. In example 1, we are given a point and we are given the slope, and we're asked to write the equation in standard form. So whatever I do at the end, I need to end up with something like this: ax plus by plus c equals 0. I know it goes through the point A, and I know it has a slope of -1/2. So m equals -1/2. Which form should I use? Slope y-intercept, or point slope formula, or standard form? Well, I'm going to use point slope form because that's what I've been given. So I'll write my point slope form. Y minus y1 is equal to m times x minus x1. I'm given the point A. That's going to be my x1, y1. And I'm given the slope. That's going to be my m. So I'll sub in what I know. Y minus -4 is equal to -1/2 x minus 3. Now be sure that you're being consistent. If you left the first y alone, then leave the first x alone. Sub your point in for y1 and x1. Okay? Make sure you don't mix them up, because in coordinate form it's xy. But when you go into the equation of the line, you're actually writing the y value first and then the x value. So here we go. Let's perform some algebra on this. Y minus negative 4 is y plus 4. And that's equal to, we can use our distributive property here. Negative 1/2 times x is negative 1/2 x. And negative 1/2 times negative 3 is positive 3 over 2. And I'm not afraid of fractions. I just leave them in there. 1 times 3 is 3. 2 times 1 is 2. Negative times a negative is positive. And carry on. Now I want to get this in standard form. So I don't actually need to move all my numbers to the right and leave my y on the left. Look, I want my x's, y's, and my constant all on the left with 0 on the other side. So let's go ahead and start moving our terms from the right to the left-hand side here. In order to move this negative half x, I need to add 1/2 x to both sides. So now I have 1/2 x plus y plus 4 equals 3 over 2. Now I need to subtract 3 over 2 from both sides. Or, because I want to be in standard form and I want a to be a whole number, I can multiply every term in this equation by 2. And won't that get rid of this fraction and this fraction? Let's see what happens. Let's multiply each term by 2. 1/2 x times 2 is x. Y times 2 is 2y. 4 times 2 is 8. And 3/2 times 2, well, let's see what that would look like. 3 over 2 times 2 equals 6 over 2 equals 3. Now I just subtract 3 from both sides. Make sure I have my placeholder on the right-hand side here. And the equation in standard form for the line that goes through the point A at 3, negative 4 and has a slope of negative 1/2 is x plus 2y plus 5 equals 0. Now I could have written this in any form, slope y-intercept form as well, so that it would be easier to graph, but the question asked for it in standard form. So we're recalling some skills. We're using all the tools in our toolbox. We've got distributive property here. We've got multiplying fractions. We've got equivalent equations. And we've got balancing, keeping everything even, doing the same thing to the left as to the right. In example 2, we're given 2 points and asked to write an equation in standard form. So again, standard form means we're looking for this. ax plus by plus c, all our values on the left, and it's going to equal 0 on the right. It's the standard form of our linear equation. We're given the 2 points that it goes through, but there's no real place for me to sub these values in here just to make it all make sense. So I need to start somewhere else. I maybe need to start with slope y-intercept form or with point slope formula. I think I'll go with point slope formula, but either way I need to find the slope first. I have been given 2 points, and I know that I can find the slope of a line. The slope m is equal to the change in y, that's y2 minus y1, over the change in x, that's x2 minus x1. Now a or b, doesn't matter which I use for my 2's and which I use for my 1's, as long as I'm consistent. Okay, I'd like to do addition here. So I'm going to make a x1 y1 and b x2 y2. It's sometimes helpful just to write those underneath to help your mind keep track of it. I'm going to work across, even though you're only supposed to work vertically, but for the sake of space, I'm going to find the slope here of this line segment AB, and we're going to have y2, which is 6, minus y1, which is negative 2, over x2, which is 1, minus x1, which is negative 3. 6 minus negative 2 is 6 plus 2, that's 8. And here we have 1 plus 3, that's 4. 8 over 4 reduces to 2. So now I know the slope of this line, which means that if I put it in point slope formula and use one of these points as my point, it doesn't matter which point I use. Here we could even draw a little sketch. I don't know if this is accurate, it doesn't have to be at all. But I'm finding the slope of this line, and I know that it goes through A and it goes through B, and it has a slope of 2. So I'm going to use point slope formula, which is right here. Y minus y1 is equal to the slope times x minus x1. And I'm going to sub in some things that I know. I can use A or B because they're both on the line. I'm going to use A. So I've got y minus negative 2 is equal to slope, which is 2, times x minus x1, which is negative 3. Let's do some algebra on here. We get y plus 2 equals 2x plus 3 in brackets. We'll distribute the right side. That's 2 times x is 2x, plus 2 times 3 is 6. And remember, we're going for standard form. So at this point in time, I'm going to start moving all of my values to the left side so that I end up with this right here with 0 on the right and my values on the left. So here we go. We're going to subtract 2x from both sides. That's negative 2x plus y plus 2 equals 6. And now I'll subtract 6 from both sides. We get negative 2x plus y minus 4 equals 0. So this is one way to write this. Generally, when you want an equation in standard form, you don't want to have a negative number as your first coefficient, as the coefficient in front of the x term. So what I might do is I might multiply both sides of this equation, every term in it. I might create an equivalent equation by multiplying this whole thing by negative 1. So if I multiply this term by negative 1, I get 2x. If I multiply y by negative 1, I get negative y. If I multiply negative 4 by negative 1, I get positive 4. If I multiply 0 by negative 1, I just get 0. So you can see all we really did there was flip the sign of each term, and nothing happens to 0 because something times 0 is always 0. So our final answer, an equation in standard form that goes through the points A, negative 3, 2, and B, 1, 6, is 2x minus y plus 4 equals 0. It's time to look at the equations of horizontal and vertical lines. Of course, in a certain sense, these are the easiest lines that you can possibly do on a coordinate plane, right? Horizontal is just a line that goes straight across and never ends. And a vertical line is a line that just goes straight up and down. No left to right movement at all. The tricky part about them is that if a line goes just left and right forever and not up and down, it has no rise and it's tough to calculate slope. Same if it's vertical. It has no run. It's tough to calculate slope. So here's the simple way to think about it. If we have a horizontal line, I'm going to use this graph to draw my A example. I have a horizontal line. It's going through the point 2, 3. Well, let's find the point 2, 3. 2 up 3, right here. Here's our point C at 2, 3. And we're told that there's a horizontal line. So if I get my ruler out, I need to draw a perfectly straight horizontal line. And you'll notice something about this line as it goes on forever never changes. It moves left to right, so its x value can change. For instance, here, the x value is 0. Here, the x value is negative 3. But the y value at each of those points is still 3. As a matter of fact, if you went forever to the right and forever to the left, the y value of any point on this line will always be 3. So the equation for this line is y equals 3. And that's enough information to draw the line forever and ever. You don't need any x here because nothing happens to the x information. No matter what happens to this line, no matter what happens to x, y is going to be 3. We don't need the independent variable x because y is only dependent on 3 if it is a horizontal line. The same rings true for vertical lines, except this time the y value can change and the x value is always going to stay the same. So we're given in B that we have a vertical line going through the point -4, 1. 1, 2, 3, 4, 1. So here's the point D going through -4, 1. And again, if we draw a vertical line, it doesn't take long to notice that it's not moving left to right at all. It's not moving along the x-axis even a little bit. The x-coordinate for any point on this line is going to be -4. If we go way up here, -1, -2, -3, -4. If we go way down here, -1, -2, -3, -4. So the x value is always -1. So all we have to do to define this line is say x equals -4. Done. That's the equation for a vertical line will always be in the form x equals something. The equation for a horizontal line will always be in the form y equals some value. You can find your homework recorded here at the bottom of the screen or at the bottom of your handout page for working through this lesson along with me. The homework problems are from page 84, 1 through 3, page 85, 1 and 2, page 87, 1 and 2. And if there are many, many examples, just pick A, C, E, G, I, and carry on. Thanks for watching.